Okay, so we got 1 through 50, Algebra 1 questions, foundational work. Need to take these problems into your next class without any difficulty. You want to look at each situation and go, yeah, I can do that, and I'll remember it. And the way you're going to remember it is to get practice in like this. Let's review it again. Whatever you don't see, eventually you're going to have trouble with. I don't care what it is in life, other than maybe riding a bike, which is a different kind of learning. You're going to forget things. So the issue here is to get enough practice and to see it repetitively enough so that you can recall. All right, so problem number 1. Let's move over here, which I am going to talk about a little bit. Write the equation of a line. -2, you write x plus 2, gets us 5. Drop in a -2, you get 5. Drop in a 12. 12 plus 2, 14. How do you get from 5 to 14? You go up 9. And so that should be our y values. You can always plug in the 12 to see if you get 14. Okay, and I think we can see the 14s, and 9 plus 5, 14. All right, so that's just a quick way to check. Now, I said something a little differently than how a textbook would teach you how to do that. So let's see how a textbook would teach you how to write the equation of a line through x1, y1, x2, y2. Okay, well, we always start with some number. I have to get rid of the first x in order to get the first y. And then when I plug in x2, I have to get rid of that subtraction. And I have to get y2, so I got to get rid of y1 and bring in y2. And that's how we get from any x to any y. That should look familiar. There was a slightly different way that I approached it, though. If you really were being mindful, I didn't do y2 minus y1. No, I didn't. It's not what I said. So how do you get from this place to this place? And it's called displacement. Except mathematicians had trouble spelling displacement like that, because that's correct spelling, by the way. They erased the TH and they put D. And so how do you get from this place to this place? That's called displacement. And what I said was, how do you get from 5 to 14? That's how I got 9. I didn't say 14 minus 5. Now you may say, boy, that's pretty petty. I don't think so. I think the essence of mathematics is to have a feeling for what's going on rather than a memorized formula. And I think folks memorize and get stuck with y2 minus 1 over x2 minus x1, and they spend so much time doing it that when we get to square problems and we turn it into a parabola, we have difficulty with that. All right, so I'll try to elaborate on that as we go along, but that's problem 1. Problem 2, mx plus b, to check your fraction work, minus 3/5 x minus 6/5. I'm sorry, I'm doing the multiplication as we go. Minus 3/5 times x is minus 3/5 x minus 6/5. Now I need to have fifths over here, plus or minus. I need some kind of fifths to express the number 4. Otherwise, I can't put these together. I hope you can see 20. And what did I want? I wanted a minus. So final answer, minus 3/5 x minus 26/5 is y equals mx plus b form, which I don't use much. All right, so 3 coordinates. So I can erase that. I can look at this and I can say, well, geez, I got multiplication. Wouldn't it be nice to multiply by 0? Because then I get minus 4. So what makes this become 0? I hope you say minus 2. And that's the change in x. So I'll change this x by 5. I think I could do this forever. I'll change this one. The y values go down 3. And I can check to see if that works. Let's go down 3 some more. Let's go way down here to minus 16. I'm going to put 18 in. And I hope you can see 18 plus 2 is 20. And 5 is a multiple of 20. In fact, it goes in 4 times. And there's minus 12, minus 4, there's minus 16. All those points work. Give you more than 3 coordinates. 5x minus 6y equals 60. Let's get some space here. The final frontier. 5x. Let's look at that a little more closely. I think that's a product. 5 times x. And if I'm going to work with a product, then I get to choose any number I want. I'm going to multiply 5 times 9.8376921044753. Yeah. Oh, no, that's not a good pick. Oh, so 5 times 0. Oh, that's a good pick. 5 times 1. That's a good pick, right? And this course is based on zeros and ones. So in this case, I'm going to put a 0 in. If I put a 0 in, I think I can solve minus 6y equals 60. And if I recognize 6y as a product, I think I can put 0 in there and get 12. I got 2 points. I connect them. I got the graph. And I'm using the x and y intercepts. On the simplest level possible, I have something minus 5 equals 9. Let me count that, not 9. Oh, yeah, it's got to be 14. It's got to be 14. So I think I can add 5 to this side to maybe see that. Subtraction becomes addition. I can do that in my head. And 7 times something. 7 times some number equals 14. I think that's a 2. So what does that tell me to do? It tells me to take multiplication on this side and make it division on that side. And I think I can see the number 2. 7/4 x plus 5. I think this thing here has to equal negative 3. I think it's got to equal negative 3. I guess I can subtract 5. And if I have something divided by 4, it's got to get me negative 3. Then this thing has to equal negative 12. 7 times x has to equal negative 12 divided by 4. So how do I see negative 12? How can I see negative 12? Oh, division by 4 becomes multiplication on the other side. And multiplication becomes division. And that's the x value for this function, which is going over 4 and up 7. And it's starting at 0, 5. And when will it hit 2? Well, it's got to be back here somewhere, yeah? It's got to be a negative number. 5's bigger than 2. Okay, so that takes care of that. There's another way I could have done that. And that is, if you don't like fractions, get rid of them. What gets rid of division by 2 and division by 5? Multiplication by 10. If you multiply a number by 10 and you divide it by 2, I think it becomes 5 times bigger than it was. If you take the number 4 and you multiply it by 10 and divide it by 2, I think it becomes 5 times bigger. Oh, 10 times 4 is 40 divided by 2. That is a true statement. And I suppose I could have done 2 into 4 and then multiplied times 10. There's lots of ways to do this. Or I could divide 2 into 10, which is what I'm hoping you see. So 35x plus 6 equals 18. And I'm not going any further because we just did that in the last problem. You can solve that one on your own. Well, do it in your head. Get some practice here. All right, so what are you going to do with it? Subtract 6, 12 divided by 35. Just put it on your answer key. All right, we got ax minus by equals c. Ax minus by, you would think it's going down, but that linear function is increasing. This one is decreasing, and we're trying to find that coordinate. We'll call it AB. How are we going to do it? Elimination is easier. You could have said y equals 3 minus 2x and plugged it in, but it's actually easier to just, I think it's easier, maybe not. I had trouble writing that 3. So 3x minus 5y equals negative 2, and I'm going to multiply this one by 5. That one by 5 gets me 10x plus 5y equals 15. And so that gets me 13x equals 13. Looks like x is 1. I'm going to plug 1 back into the function on the bottom. then I can see that y has to be 1 as well. Okay, so now I'm going to use the top and I'm going to plug 1 in. 3 times 1 minus 5 times 1, does that equal -2? And I think it does. So no carelessness, move along. It's not erase the next problem. So my function, which is another way of saying y equals 3x plus 2, and I'm doing f of 7, so I'm doing 3 times some number plus 2. That's what this function is. I should put it here. 3 times some number plus 2. That's the calculation we're looking at. So what am I going to plug in for that number? 7. 3 times 7, 21 plus 2, 23. Now I want my calculation to equal -6. Well, what is f of x? F of x is 3x plus 2. F of x equals 3x plus 2, and I want that to equal -6. Do it in your head this time. -8/3. I should be able to do that in your head. All right. You're not going to do it in your head if you write +2 + 2 or whatever. All right. F of g of 1. I'm writing it that way because I think that's how your SATs get written. I like this notation better personally. So I'm going to do g of 1. I'm going to plug 1 in and I get -2. I'm going to do f of -2. I'm going to plug -2 in, -14 plus 4, -10. Okay, now I did this one before because when I turned on Zoom, things have changed a little bit and I had to push a button that said, join the meeting. And of course, I didn't. And I got halfway through all these problems. And now I had to do them again. Okay, so this one was already done. I forgot to erase it. Difference of two squares. A squared minus y squared. Difference of two squares, you work with the square roots and you do the sum of the square roots times the difference of the square roots gives us this subtraction. So WAAP, write as a product. I'm being very specific in my language here, write as a product. In other classes, you're going to be asked to factor. Okay, and I want you to know factoring means taking sums and differences and writing as products. Now, why would we take a sum and a difference and write it as a product? Well, what if I said divide by x minus 7? And over here, x plus 7. Oh, wait a minute, what did I write 2 for? That must have been a different problem. So this should be x plus 7 times x minus 7. So it's a good thing I didn't join the video. All right, that was on the board, and maybe I made a botch right there. But difference of two squares is the sum of the square roots. So x squared in this time, it's still x squared, but this one over here is 49. So we know that that's a 7. So x plus 7, x minus 7. All right. And so if I had x squared minus 49 over x plus 7, well, I don't think I have to do that multiplication if I'm going to divide by the same number. Cancellation. Well, it's not a cancellation. You get a product of 1 or a quotient of 1, and then 1 disappears. Yeah, that's like Rene Descartes. Rene Descartes went into a fountain store there, the old-fashioned counters, you know, and asked for a milkshake, and or the attendant said, Rene, would you like a milkshake? And Rene said, I think not. And then he disappeared. Yeah. So there's your difference of two squares again. There's a 3x plus 5y times 3x minus 5y. This, however, writing these as products, trinomials, that gets me the first term. 7 and 2, I like the bigger number over here. 7 and 2 get me the magnitude. I want a minus 5x, minus plus. Doing this out and adding like terms, 6x to the 5th, minus 14x to the 3rd. I'm going to skip a little space in case I get something to the 4th in this column, right? Minus 5x cubed. Okay. Yep. Minus 5x cubed minus 5x squared. Feeling very slow at the moment. All right, so like terms, the only like terms are in this column, minus 19x cubed, minus 5x squared. If I make any mistakes, not going to start this video again. Somebody will just let me know. Maybe Yasha's still out there. We'll see. If not, I hope he's doing well. All right. Let's see. Binomial squaring. We don't want to have to do x minus. We don't want to have to write that. Yeah, put a little time and effort into it. What do you get when you multiply that? You get x squared minus 6x plus 9. All right, so there's a little jingle here, right? Double that product. You get the middle term. But don't just do this in your head. Make sure you write down everything here because these are tedious problems and it's easy to make a mistake. Take a shortcut now if you want. Minus 2x squared plus 12x minus 18 plus 5. I think it's fine to do that and move on. So that's the expansion. P of x, looking for the minimum. You should recognize that as a cup shape up. You should know that if you get the right x, P of x is another way of saying y equals, and that's what we're after. That value is the smallest y. So what's the x value? Minus b over 2a. So that's 3. If you want to understand why, go to the quadratic playlist and look at completing the square. And I'll do the geometric representations in terms of what's going on. At this stage, I'm assuming we're in good shape. So let's plug the 3 in. I'm going to take the shortcut. I'm going to get minus 18 plus 23. And so that's 5. And that's our minimum value in this case, 5. All right, so let's erase that. Hope I didn't make a mistake. The inverse, when you have a singleton surrounded by mathematical operations, the inverse is really all about solving equations. Because how do we solve equations? We do inverses. So n minus 3 over 5. And then we write it in terms of x. So our inverse is x minus 3 over 5. How do we check for carelessness? Put an easy number in. I'll put a 10 in and get 53. Over here, if a 53 doesn't get me a 10, I've made a mistake. I can see that it works. We move on. All right, let's get this off the board, save you some time. Sketch f of x. What the heck am I looking at here? I got a question. Oh, f of x equals 3x squared minus 18x minus 7. Maybe it's putting it in graphing form. I don't know. But if I'm going to sketch that, I look at the 3. I know it's cup shape up. Minus 18, so minus a minus. So 18 divided by 6, I like the number 3, I guess. I put 3 in, and if I put 3 in, I get minus 54, but cutting it in half first helps. So minus 9 times 3, minus 27, minus 7 is minus 34, and the a term is 3. Now, I like the y-intercept. 0 is to the left of 3. 0 is to the left of 3, and if I put a 0 in, I've got a gift, minus 7. Now, if you want to make sure that you're right, how far is it from negative 34 to negative 7? I didn't do y2 minus y1. How do I get from here to here? I go up 27, and if I change by 3 and square that change, well, I got an a value of 3. So this is correct. What's the sketch? We've got the sketch. What are the roots? Well, I'm measuring from this 3. Don't be confused with that. That x. I'm starting with that x, and I'm going plus or minus. How do I get from negative 34 to 0? All right, I got to go up 34 units. I've got to do what? Undo multiplication by 3 with division by 3. And I have to undo squaring with plus minus square rooting. And those are real roots. I can see x1 or x2 on this side, x1 on that. They're real roots. I can see they intersect. So I've got the roots, I got the sketch. Once you get the sketch, you've got the roots at your fingertips. A whole lot easier than solving with a quadratic formula in that instance. All right, so what do we have here? I got to go up 9. I got to divide by 3. I've got to do the inverse of squaring, which is square rooting. And I got to do the inverse of minus 2, which is plus 2. Let's see if that answer really works. 2 plus or minus the square root of 3 is this answer. And I'm plugging it in here. So minus 2 squared minus 9 times 3. Let's see if it really works. Looks like the 2's cancel. Looks like when I square a plus or a minus, I get a plus, which I don't have to write. And when I square a square root, I get what's inside. Looks like 9 minus 9. My goodness, that equals 0. Oh, well, that's a good thing because that's what I wanted. Well, this is in graphing form. This is 2x minus 0 squared plus 0 equals 18. And I think I can get this alone. On the simplest of level, 2 times what equals 18? Well, that x squared, that better be 9. So I hope you see multiplication becomes division. And squaring becomes plus minus square rooting. What's 2x squared look like? Got to know what that looks like. 2x squared goes up twice as fast as x squared. And when does it hit 18? I think at 3 and negative 3. 2 answers. Cube roots do not have 2 answers. Cube roots only have 1 answer. So you don't need a plus minus when you undo cubing. Why can't I use a square root here? Well, I suppose I could show this geometrically. That's x times x, and I want that to equal 9 times, I want a square. I want those things to be equal. Okay, I don't think that helps you see anything, but that's all right, I did it anyway. So, got to get our x's together. That's one rule about solving equations. You got to get your x's together. And then we got to find a way to isolate x. And in this case, minus b over 2a gets us a fraction. So I'm not going to put it in graphing form and solve that way. What's the easy way to solve that? Factor it. Right? And if length times width equals area, and your area is 0, then either your length or your width has to be 0. What makes that 0? 0. What makes that 0? Do it in your head. Add 9, divide by 2. Right? 9 halves. So 0 and 9 halves solve this equation. That's done. Can you factor it? Because minus b over 2a is going to get you a fraction again. Can we avoid that? Yes, we can avoid that by doing a trinomial here in factored form. All right. That gets me my first term. What 2 numbers multiply out to be 6 and are 5 apart? Well, I got a problem there because one, except that it's got to be a positive, right? So both numbers have to be negative because I'm getting a negative term. So what 2 negative numbers multiply out to be positive 6 and add up to negative 5? I hope you're putting a 2 there and a 3 there. And I'm hoping you're seeing that this function, they'll call it f of x, equals 0 when x is 2 or when x is 3. That's what you're trying to see. Here's a chance to connect again with binomial squaring. We did it 10 minutes ago, 5 minutes ago. I'm not going to write parentheses times parentheses here. I know I'm going to get squares at the end. I know those are going to be my ending square values. What's in the middle? What's in the middle is double this product. That's minus 10x, so minus 20x. I don't know why I wrote it 5 minus 2x, but I could have written it with a sign change here. 2x minus 5. So that's not the same question, by the way. But I want to do it again because that's what you're normally going to see. You're going to get a square at this end. You're going to get a square at that end. Then you're going to double that product. That's this one. I'm sorry, double it was a negative. Right? And we want to be able to spot those. We want to be able to spot these. And then check to see if that mechanics works. Okay, it's just a skill you want to develop. Oh, we're doing it again. Hope you're pausing the video as we do these. I should have mentioned that. 16a 14b squared, that's squaring this. The product is minus 20 of these. So I got minus 40 of those, double it. A7BC. A7BC, it sounds like a timeline. And then I've got this squared, which is always positive at the end, c squared. Okay, so that's binomial squaring. And it's worth learning that. You're going to save yourself time. You do not want to have to write this again as 4a 7b minus 5c. You don't want to have to do that. All right, sine of a. 5, 9. You should be able to tell me that in your head. This is 81 square units. This is 25. 20 from 81 is 61. Take another 5 away and you got 66. This is the square root of 66. Here's angle A. What is my sine of angle A? Root 66, that used to be a television show, divided by 9. What's the closest square root to root 66? I think 64. So that's 8/9. Wow. Oh, that would be 8 then. Okay, so I'm near 8 as a, right? This is near 8. Okay, so 8/9 now makes sense because the sine function never gets bigger than 1. And it's the ratio of opposite to hypotenuse. Doable. Very doable. By doing what? Making sure that these areas add up. This area is 81. This area is 25. This has to be 66. By definition, that is a square root, a side of a square. Pythagorean theorem. Why it's attributed to Pythagoras, I don't know. It showed up in history a lot earlier than the Greeks. Distance. See if you can do it in your head. See if you can look at this and go, okay, I'm looking at 36 and 16, 52, which is 2 root 13. Let's see if we can get 2 root 13 out of this as a distance. 4, 7. Let's call this 4, 7. Let's call 10, 11. 10, 11 over here. Not drawn to scale. I have a right triangle. How do I get from 4 to, that's a 10. How do I get from 4 to 10? 6 units. How do I get from 7 to 11? 4 units. What's this distance? Well, Pythagoras. So what I did was 36 in my head, 16 in my head, and that's 52. And I know 52 is 4 times 13. And so I took a square root of 4, took that out, and said 2 root 13. Perpendicular, 3 through to get x1, y1. Just generic, x1, y1. So my equation has to have x minus x1 gets me y1, and that's going to get me all my y values, right? Going to help me get started with all my y values. Perpendicular means it's given to you, minus 2 over 3, right? That's the shortcut. Right? I know many of you can take it because you've shown me that you know how. So how did it become minus 2/3? Well, we got to find the rate of change of this function and pay attention. So 77 is a constant that has nothing to do with the rate of change. The rate of change is the interplay of the ratios here, and therefore y equals 3 divided by 2 is my multiplier times x. That means if I go over 2, and I'll draw this, 1, 2, I go up 3, 1, ooh, I'm running into trouble, I'm okay. That's a 2 to 3 ratio. What's perpendicular to that? Perpendicular to that, I'll do my best job. There's my perpendicular. What did I do? I went over 2. Oh boy, did I do a bad job of a perpendicular. All right, so if I go over 2 and up 3, maybe I can do it better here. Over 2, up 3, perpendicular. I need something that gives me a perpendicular. I don't have anything. I'll use the marker right there. So there, so there, there to there. Okay. So what do I have? I have over 2, up 3. So I'm going to go over 3 and down 2. And hopefully you can see the perpendicular, a negative reciprocal. And the negative reciprocal is hiding here. Yeah, you're trying to do 140 problems in under 2 hours. You got to know your stuff. All right, let's get rid of that. Let's get rid of that. Let's get rid of that. You only seen this one day, right? But it's an Algebra 1 review. And inverse variation. So I wrote that way to see if you had any recall, even though you haven't seen it much. This is called the constant of proportionality. Inverse variation, inverse change means as x gets bigger, your original y gets smaller. So as this number gets bigger, that's going to get smaller. Let's see if it happens. So let's put the y equals 6 over here, right? That got smaller. That number better get bigger. So let's plug 3 in. Let's plug 12 in. And now my constant of proportionality is no longer unknown. It's 36. And now I can come back to x and I can come back to y. Okay, so I know my constant of proportionality. Now I can let y equal 6. Okay, and I got an equation, 6x equals 36. So it looks like my x is now 6. That's getting bigger. This one's getting smaller. Inverse variation. All righty, so what did I ask here? Probably name that tune. All right, so 1, 1 tells me x minus 1 squared plus 1 gets me 1 for a y value. How do I get from 1 to 23? I go up 22. How do I get from 1 to 6? 5, but that 5 is being squared, so 25 units of numerical change is not taking me. If I add 25 units of numerical change, it doesn't take me to 23. That's why I'm canceling it out of the problem. So 22 over 25 is rise over run squared as measured from the vertex. Why do I have to cancel squared units? Because that's what I'm getting. And now that I have this, right, it's not the friendliest number, but 0 is imaginary. Y equals 0 means my roots are imaginary, which means I'm really looking at measuring from 1 plus or minus the square root. How do I get from 1 to 0? I go down 1. The rate of change, 22 over 25. I don't know if I wanted to say that, right? But that's going to be the number. We take the minus sign and put it outside. Whatever this is, which is actually not hard to do, right? Multiplied by the reciprocal, 25 over 22, imaginary. Those are my roots. Those are my x values that in the equation will produce a 0. I suggest you plug it in and see how it works. We've already done it, so I'm not going to. Why have I asked this? MNP, solve for t. Just to make you connect with the quadratic formula, which we don't work with much. We haven't. Although it's the rite of passage in a typical Algebra 1 class. But sorry, more times than not, you can solve things a whole lot easier than the quadratic formula. But it's important to know. And I'll show you how to derive it soon. So t equals minus b plus or minus the square root of b squared minus 4 a c all over 2a. And if that square root doesn't extend all the way around, and if this fraction bar, if you truncate it and don't divide that, because the way I'm writing it right now, I'm not doing minus n over 2a. That's the minus b over 2a part. So make sure you've got the fraction bar underneath both situations, both terms, and divide both by 2m. So you don't get half a point. Probably shouldn't even give a half a point. Probably just wrong. 125 to the minus 2/3. The 3 operations, you're supposed to know what those 3 operations are: cube rooting, squaring, and flipping. I'll do the flipping last. I'll take the cube root first. So now I'm left with 5 to the negative 2, which is 1 over 5 squared, which is 1 over 25. Okay, I'm hoping you can just do that in your head in 5 seconds, write your answer on the answer key, move on. All right, so this is equal to the square root of 25 times 2 times x times y to the 4th squared times z to the 21 squared times z. What are the perfect squares? 25, 5, gone. Y to the 4th squared, y to the 4th, gone. Z to the 21 squared, squaring a square, square rooting a square means I get what's inside. Z to the 21, gone. What's left? 2xz. X minus 4 times what? This is a precursor to long division. This is the same question as this. And in calculus, you're asked to integrate that, and students have trouble because they can't write what goes in there. So what goes in here? Well, let's x squared minus 7x plus 2, x squared minus 7x plus 2. Let's do it organically. X times what is x squared? X. Now I have x squared minus 4x. I need another minus 3x to get to minus 7. How could I get x times what gives me minus 3x? Oh, x times minus 3. Of course, that gets me 12 now. How do I get from 12 to 2? I think I have to subtract 10. But we like to move that 10 inside here. So that when I do that multiplication, what happens to the x minus 4s? I take 10 away from positive 12 to get 2. Now, if you want to check this, the critical number here, what makes a 0? 4. Do f of 4 over here. And if f of 4 doesn't get us negative 10, you made a mistake. 16 minus 28 plus 2. I'm seeing minus 10. Hope you are. How do you reduce fractions? Well, division. What's the inverse of division? Multiplication. So let's write this difference as a multiplication. Looks like 10 is the common factor. That's the first rule of factoring. 10 times 3x minus 1. Oh, are you recognizing a binomial square? Hope so. Of course, it'd be nice if you wrote it properly. There. Oh, boy, I got one of these up here, 2 of them down here. I think I can cancel one of them. That's what you're trying to see. Remember, this is 3x minus 1. Let's do the foiling. 10 plus 35i, that's a 10, minus 6i, plus times a minus is a minus 21i squared. And this is where people make mistakes. They forget to write I squared. I squared is the number times itself that gives you negative 1. So I squared turns this into positive 21. That's 29i, and this is 10. Looks like my answer is 31 plus 29i. That's done. I like working with the rules of exponents. I believe I have made a statement that is equivalent to this one. And we said I squared was negative 1. I'm seeing minus 5i. F of x, 2x minus 1, g of x, x plus 4. Where do they intersect? 2x minus 1, linear function that does that. X plus 4 goes up a little less quickly. Okay, they intersect someplace at a positive x and a positive y. And if I'm going to guess here, somewhere around, I don't know, let's say 2, 7. I really don't know. You know, how much, maybe 4 comma 7, maybe 4 comma 11. I don't know, but let's find out. Let's set them equal to each other. I'm going to bring the x this way. I'll bring the x that way, 5. Okay, what did I say the first time, 2, then I went to 4? I believe that. I believe that to be true. 5 plus 4 is 9. I think they intersect up here at 5, 9. You really want to make sure you said? 2 times 5, 10 minus 1, 9. 5 plus 4, 9. I think they share that table value. I see an absolute value that is going down. I don't want to put plus minus there yet until I look and I go, oh, positive 67, minimum value, maximum in this case, x minus 2. And then I do this place to this place. How do I get from 67 to 3, 64 units of change? How do I get from 2 to 0, 2 units of change? Yeah, and I don't care if you leave it like that. It's the thought process that I'm interested in. Okay, and I hope you know it's got to be a negative. So then you're just looking at the change in magnitude. Yeah, I hope you could just write that on your answer key in 5 seconds or less. A to the minus 2, 1 over a squared. What used to be negative in the numerator is now positive in the denominator. 1 over a to the minus 2. That's a division of a to the minus 2, which we just said could have been written as a division of 1 over a squared. What do you do when you divide by a fraction? You multiply by the reciprocal. So what was negative is now positive. So what am I going to do with my negative exponents? I don't think I even gave a complete problem here. And I don't have the worksheet with me. So it probably had something akin to this. So let's put an 8 in here. Let's put an 8 to the 5 there. And let's put b to the negative 7. All right, there's the problem for us. So what do we do with this? We change negatives into the other location that's positives. So now I have 12 eighths, which we know is 3 halves, right? Each has a factor of 4 that's common. I now have that a to the minus 2 here, and there's already a to the 5 there. Therefore, I have b to the 7 here and b to the 4 here. Okay, because we usually just express with positive exponents. So I have 3b cubed over 2b7. The numbers should speak for themselves. Okay, we're going to write this as a product. How do we write that as a product? The first rule of writing products, take out what's common. Looks like they share the number 3. y4, y, they share a y. z8, z16, they share z8. What do I have to multiply this by to get back to that? Well, I got to get y to the 4. I've got 1. I've got the 3 already. I need to get 3 more of these in order to get 4. I've already got that. So a minus, I've got to get a 12. I think I need that to get the number negative 12. I already got the y. Z16, I got 8. Looks like I need another 8. That product equals that difference. We're getting there. Yeah, you could probably cut this time well in half. If you just do the problems, just say 5 root 7. And move on. How did I see that? Well, I saw the square root of 5, and I saw the square root of 35 as the square root of 5 times the square root of 7. So what I really have here is the square root of 5 times the square root of 5 times the square root of 7. Wonder what I get? 5 root 7. Okay, this is supposed to be a review, so I shouldn't have to talk about it too much. But hopefully just enough to get you to get recall. Answers. X equals 0, comma, 2/5, comma, negative 4. Move on. We've got isolated x's. Length times width times height equals volume. When is the volume 0? When you get rid of one of the dimensions. What gets rid of that dimension? What number? 0. What makes that 0? 2 inverse operations. Addition of 2, division by 5. What makes that 0? Inverse of addition, subtraction. Log base m means I'm looking for what do I put on top of m to get m to the minus 3 times m to the 7 raised to the negative 5. Well, can you see that? Yes. Minus 3 and 7 means 4. Yep. Times negative 5. The exponential activity appears to be minus 20. That's my answer to this problem. Positive 7 minus 3, was it? Yep, there's my 4 times -5, there's the exponential activity. That's what this is asking for, exponential activity in this parentheses, base M. Well, there it is. There's the exponential activity. There's your answer. All right, looks like I've got 4 graphs. How do I graph number 47? Going right back to problem number 3, I think. Plug in a 0, plug in a 0. Looks like I've got to move Renee. Sorry about that. I'm looking at this problem and I'm sketching all of these. Okay, so there's your zeros. If I put a 0 in for X, -4 for Y. If I put a 0 in for Y, 10. There's 0, -4. There's 10, 0. The line looks like that. And what did I have? A subtraction, but what kind of graph did I get? An increasing one, the opposite of that term. All right, next, 48. Well, we said you can name 3 coordinates. I can see 5, 2. I can change by 4, 9, 13, 17. I can go down up by 3, 5, 8. How many points does it take to graph a line? Only 2 of these. I could get an infinite number very quickly. 5, 2. Let's estimate it. That's 1. 5, 2 is right about there. 9, 5. Oh, that sounds like a job. 9, 5 is maybe there. Maybe a little further, but close enough for our purposes. We just discussed it. I do a little better job with the rotator cuff on the drawing. Now we're here. What do I see? Cup shape up. I'm on the downside, so I know this is going to be 0, -3. Okay, and if I want to get to minus b over 2a, -12, positive 12 divided by 4 is 3. And that is going down at 4. So if I go down 4, I'm going to be at -7, -11, -15. I think that might be -15 without doing any work. But let's plug it in and find out. I could be wrong. So if I plug in 3 times -12, I get -18, -3. So I did something a little off. So if I go down 4, -7, -11, -15. I was just playing with rates of change, and I'll have to think about that on my own time. So if we plug in 3, let's do it here. I was just having a little fun thinking about something. 3 squared 9, there's your 18, there's your -36, there's your -3, there's your -18, -3. Huh. Still gonna think about that. So -21. All right, so that's that sketch. Provided you have the vertex, you only need one other point and you can't misdraw it. If you don't have the vertex, you need 3 points. There's 3 points. What's that graph look like? The only way to draw it would be like this. All right, do a little better job. But if you got the vertex, you only need 2, because you really have a third one there, right? You really have a third one. It's the axis of symmetry is 3. So 3 that way, 3 that way. All right, last problem. V shape. 3 gets us -21. And again, 0's on this side. Put some arrows there. Put a 0 in and you get -15. Whew! There's your 50 problems of review. And I hope you can knock those out in 30 minutes or less. Okay. That's enough of that. Beautiful day here today. It's warming up. Yay. Stay safe and warm. And it's not hard to do today. You can walk around with a light shirt. It's got to be in the 60s today. It's going to snow though again. Well, that's what I tell everybody working here. When you think it snowed for the last time, it hasn't. All right. Ta-ta.